Question is, why can't we use control charts for variables all the time? To answer this question, let's come back to this example of the food company making a tomato-based barbecue sauce. In this case, we identified viscosity as a quality characteristic, and we could use that characteristic to determine whether the product was good enough or bad enough. We have our R chart and our X bar chart. Here we can see that most of the data is in control. In fact, all of this data is in control. We have our central line and our control limits for each graph. And we can use this data to ask, are there any patterns showing that the process is out of control? Let's take a step back and think about, is the quality characteristic, viscosity in the previous example, always measurable? This brings us to the definition of attribute. An attribute is a quality characteristic that can be classified as either conforming or non-conforming. We use attributes when measurements are not made because of time, cost, or need, or sometimes it's just not possible. Maybe we don't know what the quality characteristic is that we should be measuring yet. So this brings us to the definition of non-conformity. Non-conformity is, simply speaking, the departure of a quality characteristic from its intended level to the point that the product is no longer able to meet specifications. So this is when the point on the control chart, for example, is outside of the specification limits. So it's either a yes or no thing. So that means that it is bimodal. It's either conforming or it's not conforming. Which brings us to the last definition here, is a non-conforming unit. It's the unit of a product containing at least one non-conformity. Okay, so now we're ready to tackle on the first two probability theorems. I want you to write these down because in the next slide I have an example where I'm going to ask you to tell me what the particular probability is. The first theorem states that probability is expressed as a number between 1 and 0, where a value of 1 is a certainty that an event will occur, and 0 is certainty that an event will not occur. Theorem 2 states that if P parentheses A is the probability that event A will occur, then the probability that A will not occur is simply 1.0 minus P parentheses A. Okay, so let's apply these first two theorems. Suppose that we had a shipment of 35,000 glass jars. 17 jars have defective mold seams. We need to solve what is the probability of picking a jar at random with a mold seam that is not defective. So I'll give you a minute to calculate this. Pull out your calculator, smartphone with the calculator, and calculate what is the probability of picking a jar that does not have bad mold seams. Okay, so let's check your answer. First of all, the probability of having a defective jar would simply be 17 divided by 35,000, 0.049%. To calculate the probability of not having a defective jar, all we need to do is subtract 1 minus this value, and we get 99.951%. To double check our answer, all that we have to do is subtract 17 from 35,000, 34,983, divide that by 35,000, and we get 99.951%. But we need to be careful if there are more than two outcomes, and this brings us to some more probability theorems. Before moving on to the next theorems, it's appropriate to learn where they are applicable. Before proceeding to the next theorems, it is appropriate to learn where they are applicable. In this figure, we can see that if the probability of only one event is desired, then theorems 3 or 4 apply. depending on whether the event is mutually exclusive or not. If the probability of 2 or more events is desired, then theorems 6 or 7 are used, depending on whether the events are independent or not. Theorem 5 is not included in the figure since it pertains to a different concept. Theorem 3 states that if A and B are two mutually exclusive events, then the probability that either event A or event B will occur is the sum of those probabilities. This is the additive law of probability. Mutually exclusive means that the occurrence of one event makes the other event impossible. For example, think of throwing a die. If on one throw of a die a 3 occurred, in other words event A, then event B, say a 5 on that piece of die, could not possibly occur because the 3 is on top. For example, consider this problem where we have 300 parts in a box. These parts come from 3 different suppliers, and here we have columns representing how many parts are conforming, how many are non-conforming, and we have their totals here, a total of 300 parts. What is the probability of selecting a part produced by supplier X or supplier Z? Take a minute to think of how you would calculate this. All we have to do is take the sum of all the parts from supplier X, 72, divide that by 300, and then add all of the parts coming from supplier Z and divide those by 300, and we add these two terms. So we get 52.7% that will pick a part from one of these two suppliers. Theorem 4 states that if event A and event B are not mutually exclusive events, then the probability of either event A or event B or both is given by the addition of the probability of A plus probability of B minus the probability of both occurring. Events that are not mutually exclusive have some common events in common, as illustrated by this Venn diagram. Here we have the probability of an event A, probability of an event B, and in this section, this represents the probability of both occurring. To apply Theorem 4, let's ask this question. What is the probability of randomly selecting a part that is either from supplier X or a non-conforming unit? In this case, the blue represents the probability of pulling a part from supplier X. The orange represents the probability of selecting a part that is non-conforming, and this middle area represents the probability of selecting a part that comes from supplier X and is non-conforming. So we add the probability of 72 divided by 300, which is the probability of selecting a part from supplier X. We add that to the probability of selecting a part that is non-conforming, and we subtract the mutually exclusive event. In this case, there are 7 parts that are non-conforming and come from supplier X. Theorem 5 states that the sum of the probabilities of the events of a situation is equal to 1.000. In this case, all we have to do is add up all of the probabilities, and they should equal 1. But we have to be careful with events that are not mutually exclusive. In this case, all we have to do is add up the probability of each event occurring, A, B, and C, the blue, the orange, and the green areas, and then we add the areas where there's overlap. In this case, there's 1, 2, 3, 4 areas of overlap. So we'll have 7 terms, 1, 2, 3, 4, 5, 6, 7, and those should all add up to be 1. Okay, so the last problem for the day. Suppose a health inspector examines 3 products in a subgroup to determine if they're acceptable. From past experience, it is known that the probability of finding no non-conforming units in the sample of 3 is 0.990. The probability of finding 1 non-conforming unit is 0.006. And the probability of finding 2 non-conforming units is 0.003. What is the probability of finding 3 non-conforming units in the sample of 3? Take a minute to figure this one out. In this case, we know the probability of 0 nonconforming units, we know the probability of 1 nonconforming unit, and 2 nonconforming units. But we don't know the probability of 3 nonconforming units. So we punch in our values 0.990, 0.006, 0.003, and we know that all 4 of these terms add up to 1. So we punch in the numbers, we get 0.999 plus the probability of 3 nonconforming units equals 1. We solve for the probability of 3 nonconforming units, and we get 0.001. So this is a 1% or 0.1% probability. To summarize this lesson, we can't always use control charts for variables. We need to use control charts for attributes if we want to look at the amount of non-conforming product over time in a process. We defined probability, and we talked about how the calculation of probability depends on the number of desired events, the number of total events, and whether or not these events overlapped. And this is where we talked about the different probability theorems. In future lessons, I'm excited to show you how to construct these attribute charts to apply these principles of probability.